All right, guys. We're going to talk today about the situation where if our sample is not big enough to use a Z distribution, or our two samples are not big enough to use a Z distribution, what we do in place of that. Okay, so if we have a sample size of less than 30, as with all testing that we've done before, with all confidence intervals we've done before, if our sample is less than 30 and we do not know the population standard deviation, we have to turn to a t-test. Okay, and this is, as before, more real life, more applicable than the z-test. Okay, because generally we will have less than 30 samples or sample size, and generally we will not know the population standard deviation. Okay, so we're still talking about the difference between two means. I think it's not the hardest thing we've done all year, but the formulas are messy. Okay, and they're messy because there's two situations that occur when we have this type of testing. Okay, we'll get to it, but kind of give you a little bit of a preview. They're pretty nasty looking. Okay, they're not hard to calculate, and we're going to grab a calculator to help us calculate it, but it's just difficult to remember that we can either use that formula here, this top one, or this bottom one. Okay, and degrees of freedom then are found differently. Okay, so we'll talk about that as we move on. Says in real life, it's not always practical to collect sample sizes greater than 30, but still be able to test the difference between means of two independent samples. Okay, going to have to use a t-test to do this. It says the following conditions must be met for a t-test for small independent means. Okay, what we were doing in the last one was a z-test for large independent means. Okay, and we were able, because the samples were large, we were able to use the z distribution. Now, because they're small, to use a t distribution. So samples must be randomly selected. That was the same scenario, same criteria using the z distribution. Samples must be independent, same criteria as before. And each population must have a normal distribution, same criteria as before. Okay. So the standard error and the degrees of freedom of the sampling distribution depend on whether the population variances are equal. Okay. So what's going to happen here is that we're going to, even when we grab Excel later on, probably Monday, to run through this test for us, we have to make the distinction: are the population variances equal or are they unequal? Okay, and generally they're going to have to tell you that. Okay, or we make the assumption that they are equal and move on that way. Okay, but that'll be added information. I don't want to get into right now. How will I know that? How will I not know that? Right now, as we go through the problems, it will be told to you to assume that population variances are equal, which is the same thing as saying the population standard deviations are equal, right? Okay. Or if the problem says not equal, we'll adjust our formulas for that. So this leads to two different practices for determining these quantities. So the test statistic is found from the data by the following. Okay. This is exactly the same structure as before. Okay, x bar 1 minus x bar 2 is your observed difference of means. Okay, that's the mean of one sample. It's the mean of your second sample. So that's what you have observed, and you find their difference. This is the hypothesized mean of the populations. We know that's going to be 0. Okay. But you take your observed minus your expected, and you divide it by your standard error, and that will standardize our data, and that gives us our t-score. Okay, this thing here, though, okay, so lowercase s standing for the standard error of x bar 1 minus x bar 2, so that thing right there is actually an entire new formula, and it's kind of ugly. Okay, it's not terrible because It's very simple. This is exactly the same thing as what we saw with the Z distribution. We took the standard deviation, or I'm going to say the variance here because it's squared, the variance of the first sample divided by its sample size, and then added to that the variance of the second sample divided by its size. Okay? You see, this is when population variances are not equal. Okay? So population variances are not equal. So the standard error and degrees of freedom are as follows. Remember, we use a T distribution. It's a family of curves, and we need a degree of freedom to determine which curve we're using. If in the directions it says variances are not equal, that's what you're going to use as the denominator for your T, or your test statistic, your T-score. Okay? So the degrees of freedom are the smaller of the two sample size minus ones. Okay? So it says n sub 1 minus 1 and n sub 2 minus 1. You use the smaller of those differences, and that's what you use as your degree of freedom. Does that make sense? Okay? So sample, basically what that's saying is whatever your smaller sample is, you choose that and subtract 1 from it, and that's your degree of freedom. Okay? That's actually, in my opinion, that's an easier approach when we think the population variances are not equal, or we make that assumption that they're not equal. Okay? If the population variances are equal, then the info from the two samples is combined to calculate what we call a pooled estimate of the standard deviation, which we're calling sigma hat. Okay, sigma hat there. A pooled estimate is basically meaning that it's like aggregate, or a combination of the two. Okay, so what you see here is that our standard error, okay, is going to be found by taking, so it's your sample size of sample 1 minus 1, and then you multiply that by your variance. Then you add to it the sample size of sample 2 minus 1, multiply that by your variance. Okay? So it's very similar to the numerator that was up here, except for in each one of those components, you're going to multiply by the sample size minus 1. Okay? Then on the bottom, you're going to add your samples together and subtract 2. Okay? Which, if we think about it, it's the same as adding those two things together. Okay? Bless you. Okay? So that's how I find sigma hat. Now that sigma hat then becomes a multiplier for this. Okay? Multiplier for the square root of 1 over sample size 1 plus 1 over sample size 2. And then we use a degree of freedom of n sub 1 plus n sub 2 minus 2. Okay? I don't want to get in. I would argue that the creation, the formulas here are beyond like an introductory elementary statistics to talk about why these formulas are what they are. Okay? We should be able to collect all this information from our data, or if it's already processed, it'll be told to us, and we just insert it into these formulas. Okay? What we have to do is, every time we read a problem, is decide, okay, are they equal or not? Are the population variances equal or not? Okay, and that's going to then decipher which formulas to use, run through the formulas, and then we will generate our T-scores, generate our critical values, p-values, that sort of thing, and still make our hypothesis testing like before. Would you agree that this stuff kind of looks nasty? Okay, so I want to do a couple of these by hand, but then I also want to use, and we'll probably not get to this until Monday, but I want us to sit down and actually develop a Excel sheet that we can just type in, what is sample size 1? What is sample size 2? Okay, let's click a checkbox and say that the variances are equal or they're not equal, and then maybe do some conditional formatting inside our Excel that will tell us, okay, now that I've clicked this box that variances are equal, run these calculations for us. Or once I click this box that they're not equal, run these different calculations for us. Does that make sense? So that's kind of my hope as we work towards Monday to maybe start building that. It might take a couple days for us to build it, but then once we have it, It'll be like one of those things that we were using yesterday that's already built into Excel. What I don't like about Excel, and a lot of your statistical packages right now are this way, is that if I want to run a t-test on two independent small samples like this, and they give me in my problem this process data, okay, we can't use Excel the way that it's predefined in the programming with this data, okay, because it's processed. I need to get Excel to do what it does. I actually need what the values were, what the raw data values were. Does that make sense? I need to be able to put those in columns and say, okay, this is what these 20 values from the sample were, what these 25 values from this sample were. I need that information, okay? So in this example here, I would need whatever these 8 values were. And I would need whatever these 18 values were. Does that kind of make sense? Okay? It would be nice if Excel had a command that says, okay, you're going to run a 2-sample independent t-test with, let's say, population variances known to be the same, but you've already processed the data, so I can just type that in for X1, type that in for S1, type that in for N1, and the same thing for the second sample, and it processes everything for us. But nothing's built that way inside Excel right now. So we're going to build that on Monday. Does that make sense? Okay. But in order to get to that point, I think maybe it makes sense to do a couple of these by hand to show the extensive work with these formulas. Okay. We could even build something in. I don't like it, but we could build something in Desmos like this as well. Okay. Just doing it in Desmos is a little bit, I think, cumbersome. Yes, please. Why don't we use GeoGebra anymore? I mean, we could, but it's just not. Maybe. Let me see. That's a good question. Let's see if GeoGebra has a statistical test for this. So there's a difference of mean t-test for difference of means. Okay, so this is kind of what I would want to build in Excel with you, because here this is allowing us. You see here they've established that the null hypothesis is 0. We can determine what the alternative hypothesis is. Okay, do we want pooled or not? So what that means when I click that box, that means, okay, how are they going to determine the standard error? Are we going to use a situation where the variances from the populations are said to be equal or not equal? So we can choose equal or not equal. And then you could type in the raw data that's given in those tables in our problems. Does that make sense? And once we do that, it will spit out the information. So if you want to, Blaze, if I don't see an issue with doing this. Okay. So let's do one of these questions by hand, and then we can come to GeoGebra to run through and see if what we did by hand is parallel to what GeoGebra calculates here. Yes, Chuck. No, pooled is when they are assumed to be different. If population, I'm sorry, I got that back. If population variances are equal, then we use they pooled. Yes. Okay. And that's then, like I say, if you look at this question here, it says assume the population is normally distributed and the population variances are not equal. Okay. And those are things that maybe we know that the population variances are not equal because of previous studies have established that. I don't want to really. I think, again, it's outside the scope of the class to be able to talk about how we would know that they're equal or not equal. Right now, we're just going to go off of what they are telling us. Does that make sense? It's kind of like, so far all through the year, and I've hinted towards this, that they pretty much have to tell us that we're going to assume populations are normally distributed, right? Okay. Now, I've said in the past we could do things called QQ plots to establish whether my data is normal or not. But right now, we haven't talked about that. We're just going to take these assumptions right now to be true and not really worry about why they might be true. Okay. So here I've put in a kind of a flow chart for us I found this out of a textbook that I thought was pretty useful, better than, you guys remember doing this flow chart, right? Okay. I think the one I put in here is a little bit cleaner. But it's going to allow us to have 2 sample tests for independent samples. When we know we have independent samples, we know we want to test differences between them, we can run through these questions here to decide what type of test to use. Okay? So the first one says, are both sizes at least 30? Okay? If they're both at least 30, so we'll answer that yes, we can use the z-test, which we talked about in 10.1 for the last 3 days. Okay? If they're not, we're going to ask, are the populations normal? If they are not normal, then you can't do the z-test or the t-test. Okay? Because those tests are based on normality. Okay? If the populations are normal, we need to know, are both population standard deviations known? Okay, so if we know both population standard deviations, like we did in 10.1, we'll use the z-test. If we don't know the population standard deviations, we ask this question. Are the population variances equal? Okay, which is ultimately saying, are the population standard deviations equal? Okay, and again, they have to tell us that. So if they tell us no, then you have to use this formula. It says you'll use the t-test, but you'll use the t-test with this formula. Okay? If they are equal, you use the t-test with this formula. Okay? So this is a pooled, you might even want to write that on those notes. That's the situation where we refer to it as pooled sampling. All right, so this question says, the results of a state mathematics test for random samples of students taught by 2 different teachers at the same school are shown. Can you conclude that there's a difference in the mean mathematics test scores for students of the 2 teachers? So this is something that actually can be done and is done, and can then lead to maybe making decisions for that district on how maybe we get teacher 1 to produce equivalent results of teacher 2 or vice versa. Okay, maybe they can start to developing maybe similar curriculum, similar procedural stuff that might increase these scores. Okay, or it might tell us something about the way scheduling is being done that puts certain types of students in teacher 1's course and types of students or levels of students in teacher 2's course. Okay, so we could run these tests and actually give ourselves some statistical data to say, maybe teacher 1 is better than teacher 2 or whatever. Okay, so we want to first write our hypotheses, which is exactly the same as what we've always done. Okay, so it says, can you conclude that there is a difference in the mean mathematics test scores? So I don't care to determine whether teacher 1 or teacher 2 is better right now. I just want to say, are they different? Okay, so I'm just going to say mu1 is not the same as mu2. Okay, if I wanted to say whether one was better or not, I would ask, okay, I'd say mu1 less than mu2 or mu1 greater than mu2. Does that make sense? And because that's what they're asking, like, can you conclude? That's going to be the claim. Okay, and I think that's a situation when they ask you. They don't say anything about anybody having a claim at the onset of the problem or anything like that. Nobody's saying teacher 1 is the better teacher or teacher 2 is the better teacher or anything like that. So when it says, can you conclude that there is a difference, they're asking you, ultimately, is this situation which the claim? Okay, that's basically what that's stating. Okay, I think that's hard to decipher, but the word conclude, if you go through a lot of the previous problems that we've done, and just holistically overall statistics classes, when it uses conclude, the alternative hypothesis is the claim. So then we're going to say mu1 equals mu2. That's obviously the null hypothesis that we're always interested in. Okay, so it says the population variances are not equal. Okay, so if they're not equal, then what we're going to do is that we are going to take our t, because it's going to be t, because look at the sample sizes here. Sample sizes are small, correct? They're less than 30. And we do not know the population standard deviations. We know the sample standard deviations, okay? But because it says the variances are not equal, what we're going to do is we're going to use the formula that says, x bar 1 minus x bar 2 minus mu1 minus mu2 all over, okay? It's going to be the standard error of the sample, the difference in the sample means here. So that S sub x bar 1 minus x bar 2, that formula there, okay, because the variances are not equal, is going to be found by taking the square root, okay, of the variance, okay, of sample 1 divided by sample 1's size, plus then the variance of sample 2 divided by sample 2's size, and our degrees of freedom will be the smaller of the two sample sizes minus 1. So this is the smallest sample size. We'll subtract 1 from it. So my degrees of freedom are going to be 7. So as we go back up and look through this, okay, this is the idea, are the population variances equal? We said no. So then that generates this formula, okay, for our standard error, okay, and we chose the degrees of freedom to be the one that is smaller, minus 1, so 8 minus 1. Yes, please. Because when it's a t-test, the normal distribution and the t-distribution, so the normal distribution is like that, okay? The t-distribution is going to be fatter at the ends, at the tails, and lower here. And with the more the degrees of freedom, that shoots up and these shoot down and becomes more normal. So it's the degrees of freedom dictate. So there's a family of these dotted curves that are represented. I don't want to say they are similar to the normal distribution, and as that number goes up, each of those family of curves, the individual curves in the family, start looking more and more like the normal curve as that value increases. Well, when we go to Excel to process this stuff, one of the conditions will be what's the degree of freedom when we use the t distribution. All right, so find our t value then. Okay, so we're going to take the difference of our means, so 473 minus 459, minus then the difference in your means for your population, mu1 minus mu2, and that's established right here. That is saying that the difference in mu1 and mu2 is 0. If I were to subtract mu2 from both sides, I would get this phrase right here, and it would be equal to 0. So that's always going to be 0 for us, just like it was when it was the z distribution. Now the bottom is going to be this nasty looking thing, which isn't too bad. So we're going to have the variance. Now just think about this number. What am I giving you right there in the table though? Standard deviation. So I need to put 39.7, and I need to square that there. I'll divide it by 8, because that's the sample size for that first population. Plus then the 24.5. Square that. Okay? And then divide by 18. If we look at this data, what this data is saying, like collectively, by averages, it looks like teacher 1 has a better group of students, right? They're 473 average versus the 459 average. However, if we look at sample 2's standard deviation, those students are all, because the standard deviation is smaller than what sample 1's standard deviation is, the students in teacher 2's class, even though their scores are all lower, maybe collectively lower as an average, they're more compact, aren't they? They're less spread out because of the standard deviation. Okay, so they're all kind of at the same, maybe a more similar skill level or intelligence level in that class. But then we also look at the sample size and say, well, heck, that average for 473 might be that because they only have 8 people in that group compared to the 18 in teacher 2's group, right? So there's a lot of different I won't say the word is, relationships maybe that are going on here where, you know, if these two numbers were the same, and then maybe these two numbers were the same, and these were different, okay, then maybe that could tell us, just looking at the raw data, who's the better teacher, right? But because there's so many different aspects happening here, in comparison of those are unequal, these are unequal, these are unequal, it's really hard to say who's the better teacher just based off of one of these values. Does that make sense? Or one of these characteristics. This t-test should take that into account and actually give us the best answer of who is the maybe more productive teacher. So now what we're going to do is run through that with Desmos. So I said earlier we could build something in Desmos that would do this for us. The only thing I don't like about Desmos is, like, I can't save that once I make it once. I can save the URL, but it's usually not a thing that too many people do. Wi-Fi down today? All right, so Desmos, like, you could say, okay, well, I'm going to say, and now this, the only thing I don't like about Desmos is the way that we define things. I could say X1. I think I'm allowed to use subscripts here. Oh, I pushed the. I don't know, and I don't even know the benefit of that. Like, I'm not. Like, that's what I'm saying. Like, I don't know. So yeah, damn, like, that doesn't make a whole lot of sense to me. But maybe I don't know. So I'm gonna say like X1. So I could say X1 is 473. X sub 2 is 459. Then we can say S sub 1 equals 39.7. There's other ways of doing this. I mean, we could just type this in if we wanted to, but I'm trying to show you maybe if we wanted to do this for multiple problems, this will be like the quicker way of doing it. 24.5. And then we'll go N sub 1 was 8. And N sub 2 is 18. So now, because I've defined those values, when I write this formula down here, and then basically what I'm doing is going to write this formula, then I can go back into the next, for when the next problem shows up and I get another table of processed data, I could just go change these X1, S1, X2, S2, N1, N2s, and it will automatically run through and find the T value for me. Does that make sense? Okay. So I'm going to write this. I'm going to say T equals, and now I'm going to go, it's X1 minus X2, and then minus 0, and then divide by, be the square roots. Now it's going to be S I'm not sure. I think this is probably the best way to write this. Would be S1 squared. And we'll divide that by N sub 1. You want to add to it then S sub 2 squared. And divide that by N sub 2. Again, these parentheses right here are extra, not necessarily needed, but they didn't do anything wrong for me. So when I do that, we end up getting, so it calculates everything for me, right? And it gives you my t-score to be 0.922. And now, here's the thing with Desmos. If I click up here, or no, sorry, if I click right here, you see where it says share graph? If I click that, it'll give me a URL. I'm going to copy that URL. And now if I close this out, open another window, paste that URL in, it's all still there, right? Does that make sense? Okay. So if you were to create something like this in Desmos, you have the ability to save it using URLs. Or you can actually like create your own sign-in, login, whatever, and you can save like things like this. You can save little programmed things that you've made. Excel, I like Excel because I can save files and then I can put those on like a flash drive or something like that. It's not in the cloud. So t equals 0.922 in this one. So what does that tell us? Well, we go back here. We have to figure out, okay, how do I compare that then to critical values? Okay, so what we're going to do, because we wanted alpha, was alpha 5%? 10%. Alpha was 10%. So we're going to figure out our curve here. Okay. We're here, the hypothesized mean or the null hypothesis tells us t is 0. We're going to go to Excel now, and we are going to calculate the critical values. Okay, so I'm going to go t equals t.inv. Okay, probability. So we wanted a two-tailed test. Okay, and I can actually, with the commands in Excel, you can actually do a two-tailed test with typing .2t. Okay, see it says it returns the two-tailed inverse of the student t distribution. So it says probability. Well, we wanted 10%. Okay, degrees of freedom. This is where I need to know the degrees of freedom, which was 7. And it should give me that back right there. Okay, so those are the t values that we're going to use to set up our rejection region. If I didn't use that t.inv of the two-tail, what I would have to do is take the probability where alpha was 10. We had to split that in half, and that's how we're going to get those values. Okay, you see the same negative 8.9 or negative 1.89. So we get 1.89 there and negative 1.89 there. My rejection regions are to the left and right, still two-tailed test, and 0.922 showed up where? 0.922 would be there, correct? So we failed to reject that situation. Like I said, no new homework tomorrow, half hour, over 10.1, short quiz.